Hello. So welcome to the next important point in the deflection of beams, where we will be discussing about the Macaulay's method. So this is a very interesting topic because you have a lot more to do here. So when you compare with the previous topics that we have learned, it's laborious. Frankly speaking, it's laborious. You have to derive every problem is a kind of derivation, and only at the end of the derivation, if you are successful in deriving it, you will get the right answer. So be very careful, and what I wanted to say is that I need the complete concentration here. So if at any point during the derivation, if you lost your concentration, you are going to end up in trouble. So that's because we have to address the limitations of the double integration method. So we should be in a state to find out the deflection at any location, irrespective of the maximum deflection. You should be in a position to derive or find the deflection at any locations, right? So right now we are going to do that. So take a pen and a paper and try to solve it along with me. Okay. So Macaulay's method. Before we start, I want to introduce this topic. This is a particular method, and this particular method uses some strange way of solving it at some particular locations, and you have to understand how this system works, or this derivation works. This derivation works exactly like the double integration method. Here also we are doing the double integration, but we will deviate from the general integration procedure, because in order to get the right answer, such kind of off-track integrating methods has to be used, that I will explain when I solve the problem. Okay, and what we are doing here is we are defining equations for each sections. That means if we look here, we can say we can divide the entire system into two different sections, right? Two different parts, section AB and section BC. And our primary aim is to derive general equations which includes section AB as well as BC and do the double integration. So our initial aim is to obtain a general equation that contains the term which denotes AB and terms which denotes BC. Let us see how we will do that. And anyway, before starting all the problems, you should find the reactions. Anyway, for the time being, these two are the reactions. Okay, and let us name it as RA and RC. If you solve for the reactions, RA is going to be W into B divided by A plus B, or in other words I can rewrite it as L, WB by L, and this is equal to WA by L. Okay, I think you all know how to find the reactions. Now let us start from here. First of all, I will define a section between A and B. I told you that I am going to derive general equations for each section. First, I will define a section between A and B, and this is defined as the length x. So what is going to be the value of moment at x? It is very simple. It is RA into x, same as that we have derived in the previous question, RA into x. Right, now comes the confusing part. Now I am going to change the section from AB to somewhere in between BC. It can be anywhere. It can be very near to BC, but just after B. It can be very close to C or just before C. Okay, and if I define the distance from A to this section plane as x, so this is section XX. Okay, now what is the moment at x? It is, we have to consider two forces right now. One is Ra and second one is W. So it is going to be Ra into X minus W into X minus A. That means this distance is X minus A, right? Now, so we have only two sections, AB and BC. Every section we defined a sectional plane X, and at every locations, at every sections we wrote the moment equations, right? So if we compare these two equations, that means if you compare the last equation, that means the equation that we have derived for the section BC, we can see that the first term Ra into X, which is nothing but the moment of the section AB, right? If you take the section AB, the equation for the moment was Ra into X, and that particular term is reflected in the equation of BC, and that is how we have to derive the general equation for the section. So in other words, I can say it like this: if you are asked something regarding the section AB, you need to consider only the first term. You neglect the second term, because when you add the second term, that equation corresponds to the section BC, not the section AB. That means Ra into X minus W into X minus A is the equation for the section B, or for anything that is happening between the section BC. So if you are interested to find out something in the sense means deflection or slope within AB, then you have to use the first term only. So here you are not supposed to expand anything. You have to keep everything as a block. So I will say that Ra into X is a block that corresponds to AB, and W into X minus is a block that corresponds to, or the entire equation corresponds to BC, right? So this is how you have to derive the expression. For the time being, I will do one thing. I will for you just for your understanding, let's say I am defining a general beam like this, where I have two loads, say W1 and say W2, right? So this is going to be A, this is going to be B, and this is going to be C, right? Now if this is A, B, C and D, right? Now if I define the section initially at between AB, then the moment X is equal to what? Ra into X, right? Now as I told, I am changing the section from AB to BC. Now the section is here. I define the distance X like this. So if I take the section X in between BC, then how the equation is going to be? Ra into X minus W into X minus A. See? Right? So you can see that the equation for Ra into X has reflected in the equation of BC, right? Now again, if you find the moment at say CD, that means I am going to define the sectional plane here, where this distance is going to be X. Then how the equation is going to be? Same, Ra into X minus W into X minus A minus, so W1, W2 into X minus A plus B, right? So look here, if you consider the last equation, it has every term that we have defined in the previous steps. The first term corresponds to section AB, the first two terms corresponds to section BC, and all these terms will contribute to the section CD. So this is how you have to build the equation, and please don't open these brackets because we are considering every term as a single entity. So now we have derived the equation. So we will consider the second equation as the general equation for the beam. Now as I told you, we will be following the double integration method, where we are going to equate with the moment curvature relationship, which is going to be like EI into d square y by dx square equal to, what was the value of Ra? It is W into B by L into x minus w into x minus a. This is the expression, and now we are going to do the integration, right? Now comes the next important point. Okay. See, when we do the integration, don't open up the bracket. Two things you have to be very careful. The first thing is that the first term is integrated using the conventional integration formulas. Okay, integral of x is equal to x square by 2 x cube, like that. We will be using the conventional integration equations only in the first term, and the integration constants are added only along with the first term. We are not going to use the integration constants at the end, but keep the integration constant only with the first term, and you consider only the first term when you apply the general integration methods. Now the question is, what about other terms? And in those particular areas we have some difference. You consider all the other terms. That means you apply the general integration methods to the first term, use the integration constants only with the first terms. All the other terms are considered as a single block. That means you are not supposed to expand it. You integrate it considering it as a single block. That means x minus a is considered as a single block. You have to integrate considering it as x. That means let me integrate it, then you will find it easy. So I am going to integrate it. So when I integrate it, like I told, dy by dx is going to come. Now I will apply the integration principles only for the first term. That means the integration of wb by l into x is x square by 2 plus c1. Here everything is fine because integration principle is the same that we have learned. Integration constant is added along with the first term. Now I will create a fence here. From here onwards everything is going to change. I am considering w into x minus a as a single block, and I will integrate it like this. X minus a is considered as a single block, so x minus a the whole square by 2 is the equation we are going to get. Here there is no integration constant. Integration constant is added with the first term, right? Now we will do the second integration, and we will get the value as ei into y equal to same methodology, w into b by l into, it is going to be x cube by 6 plus c1 into x plus c2. So first term is associated with the integration constant c1 and c2, right? Now the barrier is there, the division is there. Now it is w into x minus a the whole cube by 6. So this is how the equation is going to look like, right? So these two changes has to be kept in your mind. The changes in integration, the position where you have to give the integration constants, right? Now you might be knowing how the procedure goes on, right? Now we have to substitute the boundary conditions. So what are the boundary conditions? Boundary conditions like this: at x is equal to 0, y is equal to 0. This is the first boundary condition, right, that we are going to apply it here. So this is the equation number 1, this is the equation number 2. We are going to apply the first boundary condition in the second equation. So 2 gives. Here another thing, the next point you have to note. See, when you apply boundary condition, you have to use the term that corresponds to the location of the boundary condition. That means here x is equal to 0 is a point that is lying between a and b. It is exactly at a, that means it is lying in the section AB. I told you previously that if you want to find something which is related to a section, use the corresponding terms only. That means here AB, the term that corresponds to AB is this one. This is the term that corresponds to AB. And if you consider all the equation, all the terms, then that corresponds to BC. Right now, the boundary condition 1 corresponds to a point in AB. So while applying the boundary condition, you consider only the term that relates to AB. So the equation is going to be EI into 0 equal to WB by L into 0 plus C1 into 0 plus C2, which gives the value of C2 as 0, right? Which gives the value of C2 as 0. Now the question is, what is the second boundary condition? What is the second boundary condition? That is very interesting. At x is equal to L, what is the value of y? Y is equal. That means here also you have the value of y as 0. Here also you have the y as 0. So this is the second boundary condition we use. Now, at where is this boundary condition located? It is located at a point C which is on the section BC. That means we have to consider both the blocks, all the terms, right? You have to consider all the terms. That means, so the equation 2 is going to give you something like this: EI into 0 equal to WB by L into x is going to be L. That means L cube by 6 plus C1 into L, right? Now we have the boundary here. W into x is nothing but L minus A, the all cube divided by 6. Okay, so when we solve this, we can say that the value of C1 is equal to minus W into B divided by 6L into L square minus B square. So kindly solve this. It's very easy for you to do the necessary arrangements. You bring everything to the left hand side, divide by L, you will get the answer. It's very simple. So you got the value of C1 as minus WB by 6L into L square minus B square. So the difficulty part is over. These are the only things that you have to be very cautious about. Otherwise you are going to make mistake. First is about the integration. Second is about the integration constant. And third and most important, how to apply the boundary condition. Which all terms you have to choose. Right? Now let us move forward. Now let us move and rewrite the equation 2. So 2 gives EI into Y equal to WB by L into, what was that, x cube by 6. So C1 is going to be minus WB by 6L into L square minus B square, right? Now comes the next block, which was nothing but plus W into L minus A, the all cube by 6. So this is the general equation. This is the general equation which you can use to find out the deflection at any point. That is the highlight of Macaulay's method. This is a general equation that you can use to find the deflection at any point. Any point is the highlighting one, because in the double integration method, I think you might be remembering what was the difficulty associated with that. But here, even though we struggled a lot in deriving an expression, but finally we got an equation which can give you the value at any location, right? Now let us see how we will find that value. Now I am interested to find what is the value, what the deflection at deflection at x is equal to L by 2. There we have the value of y equal to y max, right? This is the sub. Now the question is, which all terms you have to use? X is equal to L by 2 means it is coming in the first section area, right? not L by 2, say L by 2 means it is going to come beyond. Let us say I will do one thing. I will rewrite this equation like this. So it's not exactly at x L by 2. We will find the value of at L by 2. Before that, say it like this: at x is equal to A gives deflection at C, right? So not C, it is B. I am interested to find the value of YB, and previously we have derived this particular, I think you might be remembering, so kindly go back to that video and check the equation of cantilever simply supported with an eccentric load. This is an eccentric load, right? The equation was written over there. Now let us see whether we will get it or not. Now if you want to find out the deflection at B, then at x is equal to A means it is coming at the point B. Since it is coming in between A and B, it's not beyond B, it is at B, right? So you have to use only the first step. So you take the first step, only this first step, and you substitute the value. It is going to be EI into Y of A equal to WB by L into x is going to be A cube by 6 minus W into B by 6L divided by L minus B the whole square. There was an x here, right? Into the value of x is equal to A. C1 into x was there, so the value of x is equal to A. So when you solve this equation, you are going to end up the answer like W A square B square divided by 3 E I L as Y A, not Y A, by B. I think you might be remembering the table that we discussed, and see the equation. W A square B square divided by 3 E I L. Okay, kindly try to solve this set of equation. You will get the same answer like W A square B square divided by 3 E I L, right? Now the question is how this is beneficial. See, right now I obtained the value exactly at C and validated at B and validated that we are going to get the same answer. Now the beauty of this Macaulay's method is that if they ask you deflection at a particular point somewhere here, what can you do? Use the general equation. Right now you have a general equation. Since identify the location of the point, so here it is going to come between B and C. So we have concluded that since it is intersection B and C, we have to consider all the terms. Suppose if they ask you to find out a value at say P, which is lying between A and B, then we will choose only the first block and substitute the value of x is equal to that particular location value. It's easy for you to solve. There is no need to by heart anything. Only thing is that you should be expert in deriving this equation. It takes some time because I have derived the equation only for the deflection. Similarly, you substitute the value for in the equation number 1, you will get the equation for the slope that I am not going to solve here. You can refer any equation in a textbook, or you try to substitute the value of C1 etc. in the equation for 1. You will get can find out the slope at any location. So Macaulay's method is very easy. Only thing is that it will take some time to learn and it will take some effort. Once you master it, you're fine. You can find the value at any location. And now some interesting fact is there which we will solve later, that how can we find out the location of maximum deflection? How can we find out the location of maximum deflection? Here, even though we have found the value of deflection at B, that may not be the maximum. Maximum it is located at some different location for this, because we are not sure where it is located. Anyway, only thing we know is that it is going to come somewhere in between B and C, not in A and B, and not at B, somewhere between B and C. So it's the question is on your table. You kindly think about that. How can we find out the location of maximum deflection? Okay, you try to find the answer for that, and I hope I can explain that in one of the problems that I will solve using the Macaulay's method. Okay, for the time being, that's all for today's class. Stay tuned. Bye. And next class I will solve one question using the Macaulay's method. Bye bye.